Okay guys, so here's example 5, and again the instruction for example 5 is exactly the same as examples 3 and 4, except that I'm doing a lot of examples because these all represent different type of equations, okay? So on example 5, find the derivative at each critical point and determine the local extreme values. Again, that's the same exact instructions as 3 and 4, except they worded slightly different. So both A and B are piecewise, so let's see how slightly different they are from the first two. Same thing, we are going to start with the critical point. The critical point is the derivative, and it's the derivative when it equals to 0 and when it doesn't exist. So I want to make sure we are clear on the definition of critical point. So let's start with y prime. Y prime equals, it's a piecewise. So the first piece is 3 minus x. The derivative of that is -1, and when x is less than 0. The second derivative is, I'm going to use the power rule, so that's going to be 2 minus 2x, and that's going to be x is bigger than 0. The derivative doesn't exist here, so that's why I'm not using the equal. So if you're using equal, take it off because the derivative does not exist there. If you plug in 0, because if you think about it, the left-hand derivative is -1, and the right-hand derivative has a different slope. So that's why the derivative at 0 doesn't exist, because then one side exists, the other side exists, they're just not the same. Therefore, at 0 itself, it does not exist. Okay? Now, let's see when, so left-hand derivative, or not had, derivative at x equals 0 is -1, right-hand derivative at x equals to 0 is 2. The slopes are different, okay? So that means critical point is at x equals to 0, since the derivative at x equals to 0 does not exist. So right now we have found one critical point. Now, other critical point is when it equals to 0. Since we have two pieces, because they are piecewise, we will take each piece and set it equals to 0, but obviously -1 is never going to be 0, so we don't need to worry about that first piece. But we will take the second piece and set it equals 0 and solve for x. So -2x equals -2. X is going to give us a +1. So our second critical point is x equals to -1. Now, normally we would plug in critical points and endpoints. Okay, well, example 5 does not give us an endpoint, so we just have two values to plug in, f of 0 and f of 1. Well, let's go and see. So when x is equal to 0, we have to plug it into the second piece. So f of 0 comes out immediately to be a +3, but that's not too bad. Now, when we plug in x at 1, I have to see what that is. 3 plus 2 times 1 is 2, minus 1 squared is 1, so that's going to give us 4. So we have two places, and just like I told you before, I like to use number line to keep myself organized. We have two x locations, 0 and 1. Okay. Because we have two different places, I want to see the behavior in each interval. So I'm going to do the end behavior, -100, the right end behavior, 100, and then somewhere in the middle just to see what's going on in the middle. So when x is going to be -100, I'm going back to the original here. That's this piece. And the first term is -x, so immediately that is going to be your power behavior term, so -100, obviously. it's a negative x of a negative 100. So that's going to be a negative, oops, I forgot a negative. Negative of a negative 100, and I think the n is just plus 3. And again, I'm not looking for an exact answer. I'm just looking to see if it's positive or negative. So that's definitely positive. The right side, which is 100. Now, the highest degree term is going to be a negative x squared. So let's see what happens. And that's just really negative 100 squared. That will always be negative. Now, let's plug in a half. When we plug in a half, which piece are we plugging in? We are going to plug into the second piece, 3 plus 2x minus x squared. So 3 plus 2x minus x squared. So that's going to give us 3.75. Okay, let's see. So at 0, we know we have 3. So I'm going to put a dot right there. At 1, we know we have slightly higher than 3 because it's 4. At a half, I have it in between 3 and 4, so somewhere here, okay, this is at a half. Then negative 100, left end behavior, it's positive. Right end behavior is negative, oops, negative, and I went and write positive. So if I were to sketch this out, it would look like this. Okay, just like that. Okay, so that tells me that at 0, it looks like it's going to be your local min. And at 1, it's going to be your local max. So local min is 3 at x equals to 0. Local max is 4 at x equals to 1. Let's try again on the second piecewise. Similarly, we're going to try the same set of instructions. Find critical point, which is y prime. We are going to use the power rule. It's going to give us a negative 2x minus 2 when x is less than 1. And the second one is going to be negative 2x plus 6, and it's going to give us x is bigger than 1. So left hand derivative is going to see, so left hand, I'm using this piece, that's a negative 2 times 1 minus 2 equals 2, negative 4, and right hand derivative, I'm going to plug into this second piece, is going to be negative 2 times 1 plus 6. That's going to give me positive 4. So as you can see, they exist, but they are not the same. So our first critical point is at x equals 1. That's our first critical point. We have to also find the critical points when they equal to 0, when the derivative is 0. I will take both pieces and set it equals to 0 independently. So this first x will give me negative 1. This second x will give me a positive 3. So now we have 3 critical points. Okay? Since we do not have endpoints, if we do have endpoints, we will also use that to plug it into your original. So critical points are f at 1, f at negative 1, and then f at 3. Plug into our piecewise. So when f at 1 is negative 1 minus 2 plus 4, that will give us 1. F of negative 1 is negative 1 plus 2 plus 4, that will give us 5. And this is going to give us negative quantity 3 squared plus 18 minus 4 also give us 5. And I like to organize my information with a numbered line. So here's x. We have, let's see, the x's are negative 1, 1, and 3. So left end behavior, negative 100 is what I'm going to pick. I'm going to pick somewhere between -1 and 1. I'm going to pick 0. I don't necessarily have to pick this, but I would like to know what's going on in that interval. Then I'm going to pick also something between here. So let's pick 2. So f of 2. Those are optional because I want to know, I'm curious to see what's going on there, okay? And then this is 100. Okay. So let's go and see out of the 2 pieces from the piece Y, which one we're going to use for -100. So this is what I'm going to be using for -100. And the bottom one is what I'm going to be using for +100, okay? So let's go and do that. So -100 is going to be, I'm just going to be using the first key term, which is -x². So -100 of a negative square. Okay, so that's always going to be negative. Then the right endpoint, I'm going to use same thing. They both have -x² in the front, so I will also have a negative end behavior here. Well, out of curiosity, I want to see what's happening at 0. Well, 0 is definitely less than 1, so I would definitely use the first piecewise. So that's going to be -0, 0, and 4. So that's actually +4 when I plug it in. Then 2 is bigger than 1, so I will be using this second piece. So -2² plus 6 times 2 minus 4. That will give me 4 total. Okay, so let's plug it in really quickly. I'm going to plug all the y's in here. At -1, I have 5. So let's pretend it's right there. At 1, I have 1. So it's a lot lower. And at 3, I have 5 again. Then I pick at x equals to 0, I have 4, so slightly below. And at 2, I have 4 again, so slightly below. The left end behavior, when x is a negative, it was negative, so it goes down here. And when it was the right end behavior, it's also negative, so they both go down here. So if you look at our little sketch, it looks like this. See? It's not bad. So looks like you have absolute max, okay? All right. Absolute maximum looks like they're both 5, 5 at 2 locations. X equals to -1 and +3. Then you have one minimum right there. So you have one local minimum that was a 1 value. So that was, local minimum was 1 at x equals to 1. So as you can see, each question is slightly different, but the format I'm using is the same every time.